Okay, so fortunately, in the introduction, I'm not going to say anything that is new for you because we have told during the whole morning that developers write code that often handles secret data that we don't want anyone else to see or to obtain. And this code will run in a specific machine, and it will take a specific amount of time so the attackers can measure this time to infer the information that is secret. Now, to handle these problems, we have constant time programming, and the idea is like you don't use as a secret, you don't use the secret as an input of an instruction that might depend on the time, among other things. The problem is that in the hardware side, modern processors come with new fancy optimizations that break the security assumptions of this constant time programming, allowing attackers to obtain this information via side channel attacks. So leakage contracts have been recently proposed as a solution for this problem, as they allow us to define at the program level the information leaked via microarchitectural side channels. So we can use these leakage contracts as the guidelines to know how to write this constant time to be secure. More specifically, the leakage contracts specifies which program executions an adversary can distinguish by observing part of the microarchitectural state. So the idea is that if we have an architecture-specific leakage contracts, developers can write architecture-specific code that might not leak information. The problem is that modern CPUs are black boxes and lack these dedicated leakage contracts. So it requires a large manual reverse engineering effort to obtain this information. Our solution is to reduce part of this manual reverse engineering effort by automating the synthesis of instruction-centric leakage contracts. That will allow us to obtain automatically contracts defined as a function of the instructions. So for this, we started with a domain-specific language, where the goal is to generate constructs capturing instruction-level leaks. Again, leaks defined as the function of the instruction. For us, a contract is a set of clauses, where each clause is a conditional expression depending on the predicate. As an example, because maybe this is kind of weird to understand so far, imagine that we have a simple optimization like the register file compression on 0, which allows to map the different logical registers that are stored in the same value, 0 for example, into the same physical register. The problem is that this compression sometimes can lead to timing leaks. In our domain-specific language, we can define these kind of leaks the following way. We can observe the value after the instruction is executed whenever we have a register that is being written with a value of 0. Okay? So we implemented this approach into a tool called Malcos, Microarchitectural Leakage Contract Synthesizer. And the core idea of this approach is to use existing fuzzers to capture these leaks and automatically return the contracts specifying the leaks. So we started with the checker, which is fuzzer agnostic, so it can run in different architectures, for example, x86 or ARM. And the core goal of this checker is to find leaks. So how are we capturing these leaks? If you are not familiar with leakage contracts, we have a contract that will generate contract traces whenever we execute an input. These contract traces are the observation the contract allows to be observed. And we say that whenever two inputs produce the same contract traces, they are contract equivalent. Now, on the hardware side, we have the attacker, and the observation this attacker can make through side channels are called hardware traces. Now, whenever two inputs are contract equivalent and they produce the same observations at the hardware level, we call them, we say that they satisfy the contract, and we call them positive examples. On the other side, if it wants to continue. No? Okay, yeah. If the inputs produce different observations for the attacker, we say that this is a violation of the contract, and we collect them as counterexamples. So, given these counterexamples and positive examples, we give this information to the refiner that will generate the constraints. So it will ask the solver to find a solution distinguishing all the differences in the counterexamples while minimizing the differences in the positive examples. And with this, it will generate contracts specifying or defining the leaks that were found. We will use these new clauses to keep finding for new leaks, and we will repeat this until we cannot find more leaks. Then we will start with the contract post-processing that is split into two parts. First, we use the contract unification to set all the clauses into a single contract, and we go with the contract minimization to remove clauses that can produce over-approximations, finally returning the learned contract. We performed a preliminary evaluation where we wanted to see if the tool was able to capture leaks in actual hardware. So for that, we use a revisor as a fuzzer. For x86 architecture, we use a different subset of the ASA architecture. We use some executor mode to obtain the hardware traces by measuring the time of the execution of the instructions. And we enable speculation for the conditional branches. So with the results, we could see that the tool was able to synthesize expressions, for example, exposing the program counter for some jump instructions. We saw that for some string operations, we were able to expose the rep counter for some instructions. And also, we observed that the tool could synthesize instructions exposing when a division on 0 was happening. Also, for the rest of the subsets, we were always exposing memory loads and stores. So that's all. Thank you. I'm sorry again for all the problems.
Okay. Do we have any questions? Okay.
Thank you for the talk. I was wondering, can you generate arbitrary contracts, or is it like some templates that you can validate whether they are satisfied with by the specific CPU?
No, we don't use any template. We can start from 0, so the contracts will be generated based on the grammar. So depending on what, you can extend the grammar or not, but like you can generate any type of leak that it's able to be defined with the grammar, but we don't use any template.
Thank you. Nice.
Yeah, thanks for the talk. If I understood you correctly, you're kind of iteratively creating these contracts, right? And this made me wonder, is the end contract kind of deterministic, or does it depend on the order in which you find violations?
It is deterministic, but it's true that we have, for example, an option that is to reset the contract. Because sometimes when you are when you are refining the clauses, you find a leak, and due to the contra examples and positive examples that you are using, you are generating a specific clause. That's deterministic. But for example, that clause can be over-approximated. So we can define, okay, after running this amount of programs, you start from 0, so you can capture again this type of leaks using different contra examples and positive examples. So now the clause that you're refining, it's better.
Okay, and do you have kind of a metric for determining which is kind of the best contract that you want?
Yes, so for the first evaluation we did, we manually specify some contracts, and what we wanted to do, for example, for the constant time leakage contract, we measure how good or how far, or how close, sorry, we were from that contract. So we define like precision and soundness to be sure that the contracts that we're learning are precise and mostly sound.
Cool, thank you.
Okay, so let's just, maybe later. Sorry about that, because the time is kind of a little bit limited. So let's just thank the speaker one more time.